Hello students, I'm Miss Slate and welcome to Chemistry A. Today we're going to talk about nuclear radiation. So first off, what is radiation? In general terms, radiation is energy that's released in the form of particles or electromagnetic waves. So that means any kind of wave from the electromagnetic spectrum is a form of radiation. Anything from gamma rays all the way to radio waves. Which might be surprising because we typically think of radiation as being something harmful. But not all radiation is in fact harmful. Ionizing radiation is what we typically think of when we think of like dangerous or harmful radiation. Because ionizing radiation has enough energy to strip the electrons off of atoms and molecules. And that process can damage the cells and DNA of living things. Non-ionizing radiation, on the other hand, doesn't have enough energy to do that. So it can't remove any electrons, and so it's not going to be damaging or harmful to cells or DNA. So some forms of non-ionizing radiation: radio waves, microwaves, infrared light, and visible light. All of those are examples of non-ionizing radiation. So any waves that come from power lines or your cell phone or from light bulbs, those are all non-ionizing, harmless forms of radiation. Some examples of ionizing radiation are ultraviolet light, X-rays, and gamma rays. So these types of radiation, these waves do carry enough energy to damage cells. So this is why you can get a sunburn on a cloudy day, okay? Because the clouds only block the visible light from the sun. They don't block the ultraviolet light. And it's the ultraviolet light from the sun that actually damages your cells and causes a sunburn. Nuclear radiation is specifically radiation that has been emitted by a nuclear reaction. So this could be fission, the splitting of large atoms, fusion, the combining of small atoms, or radioactive decay, where unstable atoms spontaneously spit out particles and energy. So some sources of ionizing radiation, we've got natural sources like radon gas. This is probably the number one source of natural ionizing radiation. There's also thorium, potassium, and radium, naturally occurring radioactive elements in the Earth's crust. There's also cosmic radiation, so ionizing radiation that just comes from space that's usually emitted by stars or black holes or other objects. And then there's actually internal natural radiation from radioactive carbon and potassium in some of the foods that we eat. Man-made sources of ionizing radiation, certain medical procedures, like anytime you need to get an X-ray. Certain consumer products, smoke detectors, have radioactive americium in them as part of what makes them work. Cigarettes and like gas lanterns, like a Coleman lantern. Air travel can expose you to more radiation because the higher you are up in the atmosphere, the less cosmic radiation is blocked by the atmosphere. And then mining and ash from burned coal will also have some ionizing radiation in it, as well, of course, of what we think of normally as nuclear reactors. Now, most of the radiation put out by these sources are what we call natural background radiation. So there's always a certain level of radiation that we're surrounded by all the time. So why do certain atoms emit radiation? What is radioactive decay? So what makes an atom stable or not is its ratio of protons to neutrons. And some atoms do not have a stable ratio of protons to neutrons. You might have noticed this in the how atoms differ activity, where certain nuclei, when you built them, kind of wobbled back and forth and were unstable. So radioactive decay occurs when these unstable nuclei lose energy by spontaneously emitting radiation. So these unstable nuclei emit usually a particle and some energy in the form of waves. And when they lose that energy, they become a little bit more stable. Often they will go through multiple decays before they eventually reach a stable nuclei. There's several different kinds of radioactive decay, so different types of radiation released by these unstable atoms. And we usually classify them into 3 types. Alpha decay, which is when nuclei release alpha particles. Beta decay, when they release beta particles. And gamma decay, when they release gamma rays. So, alpha radiation is when an unstable nuclei releases slow-moving particles that contain 2 protons and 2 neutrons. We can kind of think of them as releasing a helium nucleus. Alpha particles have a positive charge. You might remember that these were used as part of the gold foil experiment. And the great thing about alpha particles is because they are big and slow, they're very easily blocked. They can be blocked by something as thin as a sheet of paper or just the clothes that you're wearing. For the symbol, we represent them with a mass number of 4 and an atomic number of 2, because they've got 2 protons and 2 neutrons. And then we either use the lowercase Greek alpha, or again, you can just write the symbol for helium, because a alpha particle is essentially a helium nucleus. So an example of alpha radiation is radium-226 will decay into radon-222 and an alpha particle. And so this is how you would actually write that nuclear equation. You start on the left with the atom that is undergoing decay, and then on the right you have the decay particle, the alpha particle, and the new daughter nucleus. Next up, beta radiation. So beta radiation is when an unstable nuclei releases a fast, free-moving electron. Again, because it's essentially an electron, it's negatively charged. And you need a little bit more to block beta radiation. Again, beta radiation can also be blocked by thick clothing, or you can use something like aluminum foil. Either way, it's still relatively easy to block beta radiation. The symbol that we use for beta radiation, we give it a mass number of 0 because electrons are so tiny that they essentially have no mass. And then we give them an atomic number slot of -1. Because part of what happens during beta radiation is that there is an increase in the atomic number of the daughter nucleus. So an example of beta radiation is when carbon-14 decays to form nitrogen-14 and a beta particle. So again, you can see that part of the process of beta decay is that the daughter nuclei has a higher atomic number than the parent nuclei. Last up is gamma radiation. Gamma radiation are high energy electromagnetic waves with no mass and no charge. Gamma radiation usually accompanies alpha or beta decay, and it can easily pass through the human body. So gamma radiation is a more potentially harmful form of radiation. It's very high energy and it's very difficult to block. In fact, you need about 3 feet of concrete or 6 inches of lead plating to block gamma radiation. So it takes a lot more than for alpha or beta. And the symbol for gamma radiation, zeros for mass number and atomic number slots, because it's just an electromagnetic wave, and then the Greek gamma. So an example of a decay that also involves gamma radiation is when uranium decays into thorium-234 and releases an alpha particle. So again, this is a form of alpha decay that is also accompanied by gamma radiation. Now we're going to go over how to actually write nuclear decay equations. So anytime you write nuclear decay equations, you're going to want to make sure you have a copy of the periodic table handy. So first, we're going to need to write a decay equation for an alpha decay of radon-212. So the first thing I have to do is I have to write the isotope notation symbol for the parent nuclei, which is radon-212. So I'd go to my periodic table. I'd find radon, it's right here. Its atomic number is 86, its symbol is Rn. So I would write Rn, atomic number 86, mass number 212. And since it's undergoing an alpha decay, one of the things it's going to emit is an alpha particle. So I would just write the symbol for an alpha particle. Then I have to write the isotope notation for the daughter nuclei. Now here's the thing that you want to remember, okay? All of the mass numbers on the right side of the equation have to equal the mass number on the left side of the equation. Likewise, all of the atomic numbers on the right side of the equation have to equal the atomic number on the left side. So I would start by asking myself, what plus 2 gives me 86? Well, 84 plus 2 would give me 86. So I know the atomic number of the daughter nucleus should be 84. So then I'd go to the periodic table and I'd look for element 84. It's polonium, so my symbol should be PO. So PO. And then once again, I'd ask myself, what plus 4 would be equal to 212? That would be 208. And then I have correctly written the alpha decay equation for radon-212. Let's look at an example of beta decay. So here it wants us to write a beta decay equation for iodine-131. Just like before, the first thing I'm going to do is write the isotope notation symbol for the parent nuclei, iodine-131. So I go to the periodic table. Iodine has the symbol I, and it is atomic number 53. So I'd start with my I, atomic number 53, and then its mass number is 131. It's undergoing beta decay, so the first thing I'm going to write is the symbol for a beta particle. There's my beta particle. Last thing to write is the daughter nuclei. Just like before, the total mass numbers on the right side of the equation have to equal the total mass number on the left. The total atomic numbers on the right side have to equal the atomic numbers on the left. Well, that makes the mass number part really easy. Well, what plus 0 gives me 131? That's 131. Then I'd ask myself, what plus negative 1 gives me 53? Well, 54 plus negative 1 would give me 53. So now I know the atomic number of the daughter nuclei should be 54. So I'd find element 54. That is xenon. So then I'd come and write my symbol for xenon, Xe. And I've completed the beta decay equation for iodine-131. And that's the basics of radiation and how to write nuclear decay equations.